Welcome back on this cold morning. Predicting whether systems at equilibrium and determining its equilibrium composition. So, what's the big deal? It's a big to-do in all this. There's a big, ugly reaction. But it's misleading. I think it's misleading because of this arrow. When is equilibrium reached? Is it reached the way this looks? This is, you can't, by the way, you can't lift a pencil, you can't think a thought without this happening. This is a complicated process in getting energy, right? It starts with this molecule glucose, and then a series of 10 steps, 10 reactions, and finally you get some energy out of it. It's crazy. But your body can do it, and do it well. So the overall reaction is what's written up here, and we've got an arrow of reactants going to products. So you add up all the reactants, they go here. Add up all the products, they go over there. So there's your overall balanced chemical equation. The question is that we're going to talk about today is, well, are you at equilibrium or not? The way this looks with that arrow, it looks like, hey, when all this stuff gets converted to this stuff, it's done. You're at equilibrium, right? And all this stuff goes away. But what's wrong with that thought? Equilibria are, just the D, starts with the D, dynamic. You're not supposed to be drawing single arrows. You're supposed to be drawing double arrows. In fact, it's even kind of better if you draw something like this to kind of illustrate where the equilibrium lies. That's kind of the terminology, where it lies. Well, if it lies mostly with product, well, then you draw a bigger arrow going forward than you do going back. But the point is what's not changing when you're at equilibrium? What's not changing? The overall what of each compound in that reaction? In that equilibrium, the overall concentration, the overall amount. Right? It's not changing over time. Then you're at equilibrium. And whether you have more product or more reactant, that's just the reaction itself. They're all different. You don't know. Okay? So what we're going to do today is we're going to be given a whole bunch of, they could give us the amounts of all these guys. And then they say, hey, are you at equilibrium or not? Okay, well, we're going to figure out how to answer that question. And then we're also going to say, hey, you're not at equilibrium, so you're going to generate more product to achieve equilibrium. Or you're going to generate more reactant to achieve equilibrium. So we're going to be able to make those predictions. Okay, and we'll also play around some more with actually getting the equilibrium composition. Okay. Oh, and remember, so Steph, do you remember that? What's the equilibrium composition? That's the fancy words for doing what? For giving, what would be your answer when they say, hey, the equilibrium composition? What are they after? We might, but they're after the final answer, the concentration of everything there, right? Yeah, you're going to have to do ice. When you see equilibrium composition, what's the equilibrium composition? Man, you know ice is coming, right? So, because you have to give that E row. There's all your answers at equilibrium. That's what you have to give. So the only way to get it is to do ice. All righty. Let's do a little review quick, though. With the symbol for the equilibrium constant being Kc, Mia, what does the C stand for again? That little C probably stands for what? That would be good, but it doesn't stand for constant. Concentration stands for concentration. Okay. The one and only way, Alyssa, to change Kc is, this is a hard question. Maybe it was in the reading, maybe not. Because they're fixed in stone. The only way to change is to change temperature. And then these equilibrium constants change on you. So if you're ever given an equilibrium constant, they pretty much have to tell you what the temperature was. Otherwise, it doesn't make sense. You're going to have a different equilibrium constant. Okay, so that's getting more complicated than where we're at. But if you're a chemical engineer, you're keeping your system at some constant temperature, so you know what these equilibrium constants will be. You can make better predictions. The equilibrium concentrations at 25 degrees Celsius for the Bowl reaction were found to be What's a value for Kc at this temperature? Megan, what do you think we got to do here? Okay, Kc equals, what would you write? Ca plus 2. Oh, the product side, all right. That calcium hydroxide, funky compound. Squared. Put the reactants. Look good? Jose, did I forget something? Or does that look good? Little 3 on the hydroxide, good. Yeah, there you go. Okay. Okay, Kenneth, now what would you do?
Fill those into the values.
Yeah, fill in those values. So are we doing ice? No, they just wanted a number for Kc. So we're going to do exactly what Kenneth said. We're going to plug in all those numbers and get a number for Kc. The calcium hydroxide compound was 2.5. Has to be raised to the second. Calcium is 4. That has to be raised to the second. Hydroxide is 2.5. That has to be raised to the third. See if you can do all that in one step on these calculators. If you can, you're doing pretty good. 2.5, I'd push the x squared button. Divide by 4, push the x squared button again. Divide by 2.5, and I can push x to the y and get it to the third, or I can push the cube button. That's orange. Shift x cubed equals. Anybody get an answer? What'd you get, Audrey? I didn't get 6.1. Maybe I did it wrong. I got 0.025. Oh, okay, made me feel better. Okay. Make sure you can get this, 0.025. So 2.5, hit the x squared. Do it all in one step. Don't be writing anything down. 2.5 squared, divide by 4 squared, divide by 2.5 to the third. Oh, no, no. Do it all in one step. You're safer, and it's less frustrating. You get homework will go a lot faster. Okay. So 0.025. Enrique, you got it?
Yeah.
All right. 0.025. So after our little review, there's 2 types of problems that we're going to see. How can you predict if a reaction is at equilibrium, and if it's not, will more reactants or products form to finally reach equilibrium? So I've changed this a little bit this morning, but it's the same essentially that you have in your notes. What's the answer? How are you going to do this? Kendall, it says the answer is 2. What are we going to do to solve this problem? Predict if a reaction is at equilibrium. And if it's not, will more reactants or products form? What's the answer? How are we going to do it? The answer is QC. Calculate a QC. Okay, well, it's called reaction quotient, right? But no worries. Bowdy's going to tell us all about this. What is a reaction quotient? QC. What is it? Now there's a little hint. Andrea, there's a little hint. We're going to be comparing it to Kc. So what would you guess QC is? Yeah. So they're going to give us kind of, you almost have to imagine the question. You got to predict if you're at equilibrium or not. And if not, which direction is going to shift. So in other words, they give you a reaction. And they give you every single concentration of everything. Somebody analyze it. They know the concentration at this moment in time of everything. And they say, hey, is that at equilibrium? If not, are we going to get more product? Are we going to get more reactant? What's going to happen? you calculate Kc. Pretend it's at equilibrium. But you don't know what's at equilibrium, so you can't write Kc equals products over reactants. You have to write Qc is products over reactants. So you write a Kc expression. Exactly like you would do if it was at equilibrium. Concentration of products raised to their stoichiometric coefficients divided by the concentration of the reactants raised to their stoichiometric coefficients. Divide them out and get a pretend Kc, except you call it Qc, reaction quotient. So you get that number. It's going to be some number. Just like Kc is a number, right? These guys are both numbers. They got to tell you what Kc is. Okay. So you calculate this pretend equilibrium constant called the reaction quotient, and let's say it's bigger than Kc. It's bigger than what your equilibrium constant was, right? It's kind of like, let's say Kc is, I don't know, 18, and you get your Qc and it's 106. I'm just making it up. Okay, so your Qc is bigger than what the actual equilibrium constant is. So Andromeda, does that mean that there's too much product or reactant? If our Qc is too big. There's too much product. Because these equilibrium constant expressions are what over what? Products over reactants. So if its number's too big, you have too much product. So if you have too much product, which direction, Enrique, would you say this equilibrium is going to shift? Is it going to shift towards reactants, or is it going to shift towards products? Yeah, we have too much product, so it's got to go the other way. Exactly. So if you have, remember, so you got reactants going to products. If this is too much, you got to go that way. Okay. It's that Le Chatelier's principle. All right, I'm not pronouncing that guy's name right, but that's the idea. If Qc, Connor, is less than Kc, now Qc is only, I don't know, 6. Kc was 18. Now there's too much reactant. So everybody, we got to shift towards products. All right? So that's the game we're going to be playing. But there's a third possibility, Jose. Man, they're both 18. Then what? They're the same. What does that mean? You're going to shift towards both sides equally, or just there is no shift, right? It's at equilibrium. Things are hunky-dory. They're going to stay at these concentrations. The concentrations of the reactants and the products are not going to change. You're at equilibrium, however you'd like to say that. Okay, we found Kc in the last expression to be, I think it was 0.025, right? Okay, so that was our Kc. However, you monitor all these concentrations. You have these little sensors and all this stuff going on, and they want to know if you're at equilibrium or not. Look at all these concentrations they give you. Those concentrations, 2.6 and whatnot for calcium, they're definitely different than these. But they could have just started out with a whole different amount here. Andrea, what do we do to answer this question? Are we at chemical equilibrium? Set it up the way you'd set up the Kc expression. Exactly. Except don't write Kc, write Qc. Products over reactants. We had that calcium hydroxide compound on top. And that was squared. And we had calcium ion on the bottom, and that was also squared. We had hydroxide, but that was cubed. So plug them in. See if you're at equilibrium or not. And if you're not at equilibrium, predict the direction that the equilibrium will shift, that the reaction will shift. And there's no way you got .025, is there? What did you get?
0.0252.
What'd you get?
0.0252.
You got .0252. Really?
Yeah.
0.038? I hear a lot of .038s. Can look up .038.
That's what I've got.
Try it again. 13.4 squared, divide by 2.6 squared, divide by 8.9 raised to the third power. So does everybody agree with the .038? Okay. So what did you circle? Are you at equilibrium, everybody? No. And you are going to shift toward draw the arrow to this way or that way. Draw it to the, what is that? Right? Left? Yeah. You've got too much product. Okay. Problem 2. Here's the second type of problem. So the first type of problem was, hey, are you at equilibrium or not? And if you're not, hey, what direction is this reaction going to shift? You can get more reactants or product. Here's the second type of problem. They give you Kc. And they give you a reaction. They want to know what the equilibrium composition is. So they're just giving you one number in this problem, and that number is Kc. What's the equilibrium composition? The answer is do blank, but with a blank table. I know I did change it. I made it more fancy looking. Do, what 3 letters? Ice. Do ice, but with a what table? Concentration table. So much easier than using a mole table. So we're going to do ice, but with a concentration table. So it's a lot easier to look at that type of question. They have a 1 liter vessel, contains, oh, I give you a lot more numbers than just Kc. 1 liter vessel, yeah, if they didn't, you wouldn't know what's in the initial row. 1 liter vessel, 3 moles of chlorine, 5 moles of bromine, they're mixed. The equilibrium constant, Kc, is 50. What are the final equilibrium concentrations? So they could have said, what's the equilibrium composition, like they did before. Okay, so we're supposed to do ice, but with a concentration table. Cameron, do ice, but with a concentration table. So what would you do here? What would you start out? Well, I would make the table, right? What are the columns? Ice, that's what I would do first. Because that kind of guides you. Then what? Yeah, fill out which row? Yeah, fill out the I, right? Except we don't want to put in moles, right? You want to put in concentration. So if you want to put in concentrations and not moles, Kendall, what would you put in that I row?
Do I have to use the liters?
Yeah, because big M was what over what? Number of over number of, yeah, moles over liters. I made the numbers easy for you, right? Because the volume is just 1 liter. So going across the bottom, everybody, chlorine will be 3 molar, 3. Bromine will be 5 molar. Bromine chloride, nothing, right? Didn't say anything. If they did, we would write it in. The change row. Steph, how do we do this again? The change row? Subtracting and adding. Yep. The coefficient times x. So this would just be x, or would it be 3x? Just x. Everybody under bromine is going to be x. Under bromine chloride, 2x. And then you add stuff up to get your answers. 3 minus x, 5 minus x, 2x. Remember, these are your answers at equilibrium. Here's your composition. Here's your equilibrium composition right there. Those are all your answers. Just got to figure out what x is. If you figure out what x is, man, we're done. Just plug it in. Okay, Mia, how are you going to get this x? Take that equilibrium constant, which is 50, okay.
And 50 equals 2x and 2 divided by
Ooh. 2x all over
2 divided by 2.
Now this is where you can jump right to what Mia's doing, but it's kind of dangerous if you haven't done this a lot. It's a lot safer, I think, to write, because it doesn't take very long, to write that equilibrium constant expression. Kc equals, products over reactants, all that bracket stuff. Because then you don't make the silly mistake. The silly mistake in this case might be forgetting to square the 2x. And you go through all this work, whether it's a quadratic equation or not, and oh gosh, you just made one silly mistake after all that work. So I strongly suggest doing this first. It doesn't take very long, but it's like insurance. Because hardly anyone ever screws up when they write this part, even with the exponents and things. And then you just plug them in. And that's why we made a concentration table, so we can directly take the stuff from the E row and put it in here. So take that stuff from the E row, put it in the Kc expression, and then you got a little algebra to do. Give it a shot. Now you'll see why we practice the quadratic equation. Yes, you should do moles over liters. We want to make a concentration table. But our liters were all 1, so I made it easy. But the homework's not going to, I'm sure. I bet the problem after this won't have 1 liter. I think this is about as ugly as it's going to get. If you can handle this, we're going to be doing good. Right. Yeah, and then you got to remember that quadratic formula. Remember it? negative b. Whoop, ax squared, right? So that's the goal. Did you get that for your A, B, and C? And A is 46, B negative 400, and C 750. So you can go ahead and use these for A, B, and C. If you want to make the numbers smaller, you can divide through by like 46. But it's all good. I think it's just easier to use the numbers that are here since we have a calculator. So I got 400 plus or minus 148 over 2 times 46. So that square root part, I got 148 for it. So did anybody get those two possible answers? 5.96 or 2.74, depending on how many digits you carry. It should be somewhere around there. Okay. Hopefully you got that. And then they wanted to know what are the final equilibrium concentrations. So again, here's all your answers. Just plug in what x is. But you have two x's. Which one do you use? Which one do you use? Usually it's easy to pick which one to use because x won't never be negative, right? Because you end up with these positive x's as products. You can't have a negative answer, negative concentration. But this case, they're both positive. So which one do you pick? Only one of them makes sense. Like Megan, you said x is 5.96 or the 5.91. If you pick that one, you get negative answers for concentrations. So you can't pick that one. That one's your garbage one. So you have to pick the smaller one. So plug in 2.74. So we've got chlorine is 3 minus x. What was the other one? Bromine is 5 minus x. And bromine chloride is 2x. So to take that 2.74 and plug them in, you'll get about, what, 0.25 or so, 0.26 for chlorine. About, what, 2.25 for bromine. And 2 times 2.74 is about, don't screw up, about 5.5. Okay. All right. And then so you don't go through all that work and get points taken off, what units do you put on your answers? Big M, molarity. Good. So you see how we did it? We made an ice table, put in the initial concentrations, completed the ice table, and notice how writing that Kc expression it's a lot of work. If you screw up writing your 2x squared divided by 3 minus x over 5 minus x, if you screw up there, everything is messed up. So I think I look at this step as insurance. I wouldn't skip it. I think that's an important step. Okay. And we did our algebra. We broke it down until we got it in the form of ax squared plus bx plus c equals 0. Figure out what our a, b, and c are and plugged them in the quadratic formula. We picked the x that made sense. The other one gave a negative answer. And then we plugged them all back into the E row. Here's a conceptual question. Mia, we get a break from the homework. I mean, calculators anyway. And it's a conceptual question. We're supposed to be able to know the answer just by reading it. Solely on the basis of the value of Kc, decide whether or not you expect nearly complete reaction at equilibrium for the following reaction. Now, let me ask you this, Mia. What do you think nearly complete means? Nearly complete. Anybody having a guess? Yeah, what would it mean if it's complete? You'd have a lot of what and very little what? A lot of product and very little reactant. That's what they mean when they say nearly complete. It's kind of stupid, right? I mean, either you're at equilibrium or you're not. There is really no complete idea. But they're just saying English is hard. So nearly complete means, hey, this is a reaction where you get a lot of product, very little reactant when you reach equilibrium. That's what nearly complete is. Not all reactions fit that category. Okay. So is that the case for this reaction? Audrey, you're shaking your head no. You're right. Yeah, you're right. How did you come up with that conclusion? Yeah. Anybody know? No, you're supposed to look at KC to figure it out. KC is really small. That's what you're supposed to do. You're supposed to look at this number for KC. And it's really, really small. So that means, do you have a lot of product? I always think of the amount of product. Do I have a lot of product? My numerator is going to be, my numerator is the product, right, in the KC expression. KC is product over reactant. So do I have a lot of product or a little product? If KC is really small, I have very little. So that means it didn't go to completion. I mean, it doesn't fit that category. So no. Okay. So see if you can set this one up. I don't think you're gonna have time to solve it unless you're really good at this stuff. All right? See if you can set it up. Setting it up is the most important part anyway, probably. See if you can set up 70. Then we'll call it a day. What's the temperature doing in there, Kenneth? Does that mean anything?
No.
No, it doesn't. All right. It just, I guess it's a good idea to say it because that's the only way to change that equilibrium constant. But you don't even need to know the temperature. Just make sure it corresponds with whatever K is. You end up with an expression like this, like 49 equals x over 0.1 minus x times 0.1 minus x. if not, see where you messed up. And then you'd have to actually do FOIL, do your FOIL, right, or whatever you like to do. End up solving for your x. So we're about out of time, but that's the idea. So come by and I'll be glad to help you out with these problems.